Okay, we'll get started again. Hope everyone had a good lunch, and we have two exciting talks coming up next. Hopefully, no one will go to sleep after a nice lunch. So, the next speaker is Nick McKeown. Nick is a professor of computer science and electrical engineering at Stanford University, and he's chief scientist and founder of Barefoot Networks. I'll hand over to Nick.
Thank you very much, Deepak. I'm Nick. I'm going to be talking to you about programmable forwarding and telemetry. But before I start, I wanted to thank Albert and Deepak for hosting us today. Thank you very much for inviting me. I think this is a great idea to have an event like this. I think we need more conversation about how we build networks and how they're evolving for the cloud. I spent the last 10 or 12 years thinking about how networks be architected with one goal in mind, and that is, how do we enable the networks generally, the internet in particular, to be controlled and for their operation to be determined by those who own and operate the network? Seems like an obvious thing to do. Every other piece of IT infrastructure, its behavior is determined by those who own and operate it, computation, storage. But in networking, it's been the chip vendors and the equipment vendors who have dictated how the network operates. And so over the last few years, with what was called SDN, which I kind of refer to as Act 1, it's in which network owners have now taken control and taken charge of their control plane. And so over the last few talks, it was just taken as a given that those who own and operate networks, whether it's Microsoft or Google or Facebook, they write the software that determines how it's controlled. That was a controversial thing to say 12 or 13 years ago, and people would roll their eyes when you said it. And now it's out there everywhere, every day of the week. And in fact, you take it for granted that they can write that software, or they can commission somebody else to write it, or they can buy it separately, or they can simply download it off the internet and then modify it to serve their needs with something like Sonic or FBOSS, etc. So that has been going on for a while now. So it would seem as though now finally I can tailor my network to meet my needs. Surely I can quickly deploy new protocols. I can monitor precisely what my forwarding plane is doing. I can fold expensive middlebox functions into my network for free. I can just simply add them into the network infrastructure. I can try out beautiful new ideas. I can unleash that sort of Cambrian explosion of ideas from the software developers to deploy into my infrastructure to bring about change that I wasn't able to before. I can differentiate. So if I'm AWS trying to compete with Azure or Google Cloud, then I can differentiate by changing the behavior of that network. And I can own the intellectual property. I don't need to give it to my equipment vendor. I don't need to give it to my chip vendor. But wait a minute. Every single feature that I just listed, you can't actually do that, because it's not in the control plane. You all nodded when I said that, right? That is the deception, the kind of the crock of networking. So much is baked in. It's either baked in through the equipment from OEMs or baked in through the chips themselves. And so what I've wanted to do is to try and liberate that and place that control, that ability to define the behavior in the hands of those who will innovate, because that will make networks more reliable, more secure, and over time, just make them better. So let's think about why this is. This is a cartoon picture of a piece of networking equipment. It has a switch OS, typically Linux-based, a driver, a switching chip, and then features that sit on top, such as OSPF, BGP, etc., that people will use in their network. Now imagine that it's 2010. Cisco and VMware have just defined VXLAN. All right, so think about how these packets get processed. There's a pipeline that sits down in the chip. Packets will come in. Headers dictate the layer at which it will be, the stage in the pipeline at which it will be processed as the packets pass through. You want to add that new feature, like that VXLAN feature. What do? You just add a bit of software on the top. You can describe VXLAN in about a page, about 5 minutes. Very simple. To write the software to control VXLAN, it's a couple of weeks' work. How long did it take to deploy? Well, it needed an extra layer of processing in that pipeline. So from the time it was defined to the first time it was deployed was 4.5 years. Why is that? Because it had to change the hardware. because the hardware function was fixed. This was not a niche application. It was in the most invested in, the most profitable, the fastest changing part of the networking industry. And it took 4.5 years to add a new feature. That little yellow header that I got added there, that innocuous little yellow header, the VXLAN header, being processed by that extra stage, was a very complicated thing to add into the ASIC. What is the dynamic that goes on here? The network owners get together. They tell their equipment vendors, hey, I'd like this behavior added to my network. They all huddle at the ITF. Everybody has to build up the confidence that they're not going to be the only idiot that does it and then look like a fool because they've invested in the wrong thing. To invest in a new chip takes about $100 million. You're not going to do that unless you're pretty sure that other people are going to use it. You need it to be standardized. You need everybody to agree. So there goes the differentiation. You then go and ask the software team, how long will it take you to add this new feature? Yeah, maybe a few weeks. And then you ask the ASIC team, either your native ASIC team or a merchant silicon team, how long it will take. That new feature will take years, and that's where the long pole in the tent is. So when you need a new feature, your equipment vendor, they can't just send you a software upgrade. New forwarding features take years to develop. By then, you've figured out some kind of horrible kludge to work around it, and we've all seen those kludges. And your network gets more complicated, less reliable, more brittle. It's less likely to work. Eventually, when the new chip is available, the new upgrade is available, you've either decided you don't need it anymore because you found some way around it, and all your software on top, it depends on that kludge. Traceroute, for example. Or you need a forklift upgrade in your network, expensive, in order to replace that. We all know this. This is because networks are built bottom-up today. And we're all used to it. And I want to challenge you to think, why on earth is that the case? The software on my computer doesn't work bottom up. I write a program, and then the feature actually is compiled downwards to tell the computer what to do. In networking, the chip tells me what to do. If you want to build a piece of networking equipment, you have to go out and survey all of the different data sheets. And the data sheet says, this is how I process packets. And I'm different from the chip over here that processes packets in a different way. That data sheet, usually a book, is written in English, ambiguous English, that you have to try and wade through and figure out, does it do what I want? How do I actually force it to do the things that I need to get done? So as a consequence, the decision as to what your network does is being dictated from the bottom up. And it fits well with the conventional wisdom that has been around for a long time. I myself are guilty of having perpetuated this for a while and saying programmable switches, those which will allow you to determine the behavior from the top down, are 10 to 100 times slower or consume more power or cost more than fixed function switches. Act 2. And this is what I've been spending a lot of my time on for about the last 7 or 8 years, is trying to disprove that conventional wisdom. And now I can say, I totally believe that conventional wisdom is 100% wrong. It was right at one point, it is no longer true. Actually, nothing because I've done. I think it was just an inevitable change of the technology. And today I want to tell you about why I think that is. So this Act 2, which is now underway, network system developers are taking more control of the forwarding plane too. To put it in cartoon fashion, what it means is the arrow changes, and we're going to start programming it top down. You define the behavior that you want. You've probably all heard of the P4 programming language. It's just an example of a language, but a language that allows you to efficiently specify a behavior that you want, which is then compiled down, top down, to tell the switch what to do. That could be a physical switch, it could be an FPGA, it could be a SmartNIC, it could be the kernel of an OS. All of those are practical. So why is this happening now? I mean, everything I said so far is kind of obvious. So why is this happening? Why is this happening now? I think it's because we were jealous. Everybody else was doing it, and now we're trying to get in on the act, right? So we've had the computer. You write in high-level language like Java. You don't have to tell Intel what you're doing when you write your Java program. You just write the program, whether you're Facebook or Google, and you write that program and then compile it down. It's been abstracted away. The registers, the instruction set has been abstracted away. Sorry, do I have to tell Intel when I write Java? No, OK, all right, just checking.
We already know.
Oh, OK, good. They already know what we're doing. Then for graphics, I remember you remember graphics cards that look like this? A whole load of chips. I can remember the debate. Would there be some time in the future when you could build a programmable device that would be fast enough that you could do graphics right by writing programs? Partly it shows my age, but it was a genuine open question. And then in a period of about 1 year, all those big cards went away. What happened? somebody built a domain-specific processor with a specialized instruction set optimized for graphics and a data path model internally that exploited the parallelism present in graphics applications, and then developed a language, several languages, that would allow you then to write efficient programs that could be compiled to run blazingly fast on that GPU. Everything was over. You don't see discrete graphics cards anymore. You'd be crazy to do it. Same thing happened in digital signal processing. When I was a student, a long time ago, people were debating whether signal processing, things like radars, video coders, things like this, would be built out of discrete components, or maybe somebody would come up with a processor, a domain-specific processor. Well, that's also called a DSP, a digital signal processor. Today, you wouldn't think of doing it any other way. You have a high-level language like C or MATLAB. You go through a compiler that abstracts away the instruction set, the parallel forwarding model, parallel model inside the DSP chip to allow you to write whole new ideas. And we've seen the applications in graphics that have exploded. GPUs get used for everything now, machine learning, autonomous vehicles, DSP chips used for everything under the sun. We're seeing the same thing in machine learning. This was created when there was really only one that people were talking about. There's about a half a dozen I heard about last week alone of new processors designed for this. They're domain-specific processors with clever instruction sets, new models of parallelism to try and abstract a way through a compiler to a language. So why hasn't this happened in networking? So as soon as I say this, your brain pattern matches on processor and says, yes, we did. We had NPUs. That's what a network processor was. Great name, but actually not really. All of those other devices, they had instruction sets that were deliberately, carefully designed for their domain, and a language that was carefully designed for their domain. In networking, most NPUs were a bunch of RISC cores thrown onto a piece of silicon. Packet would come in, you'd find one that was free, and you'd send it to it. Programming was done in C, no domain-specific language, no specific instruction set. So nice name, but it didn't actually work out in practice. They were slower, they were hard to program, and to a large extent, they've gone away. So what we've been trying to do is move this forward in a way that's really continuing the work that was done by Fulcrum and from others in trying to see how you can design a domain-specific processor that has an instruction set and a model for the data path and parallelism that fits well with the domain, tie it with a language that will abstract away the underlying machine. And that we call the PISA architecture, or Protocol Independent Switch Architecture, and the language that we've been working on, P4, Programming Protocol Independent Packet Processors. That's what the 4 Ps are. The PISA architecture, this is a cartoon of it. This just shows 4 identical pipeline stages. The red lines on the left are the incoming packet lines, they're the ports. The ones on the right are the outgoing ones, and then the buffers on the right-hand side. When packets enter, they will first see the parser. The parser is saying, OK, let me see where this is a legal packet, find the headers, figure out how to break it up so I know how to process it correctly. And then it goes through a number of identical phases, and stages. You've heard about match action pipelines, match plus action in each one. The parallelism through the pipeline means that each stage of the pipeline is processing a different packet, so we get parallelism in the left or right dimension, and parallelism in the vertical dimension, because within each packet, different headers can be processed in parallel, as long as they're not dependent on each other. So 2 dimensions of parallelism, which suits the problem very well. In a way, this looks somewhat like the pipelines of fixed function devices. It's just in fixed function devices, each of these stages is dedicated to a particular role. Here they're not. They're all identical. They know nothing about networking. They know nothing about the application that they're running. They just have an instruction set. Just to give a sort of a cartoon view of how this would work, imagine a packet coming in, different headers. The parser has been programmed by the user to say what kind of packets to expect and what kind to generate. And when it sees it, it's essentially typing those headers. And as it types those headers, it will then rip them apart. So this is now moving to how it electrically works, actually separate them out, put them and present them to a variety of different memories, depending on the header. One header could be MPLS, another one could be IPv4, the other one could be IPv6. They can perhaps all be done in parallel if they're not dependent on each other. One thing to observe here in networking, there is surprisingly little serial dependency amongst protocols, because the protocols were largely designed to be orthogonal from each other because of layering. So there's actually less serial dependency than you might imagine. I show 4 stages here representing 4 potential serial dependencies. In practice, you would use more than that, but you don't need hundreds. It's typically in the range of 10 to 30 is the number of stages that you would need, depending on the environment. This first stage, these headers get presented to the memories for matching. It could be exact match, ternary match, whatever is needed. And then they go through, and then the ALU will perform some operations on it. It could decrement a TTL, update a checksum. It could encapsulate, it could decapsulate, create new header. So I show a different set of headers after it's gone through this. It's essentially been transformed by that first stage, under the direction of the programmer who said how that transformation was to take place. And then that packet, those headers from that one packet, will progress down that pipeline and be transformed as they go until they reach the other end, and then they're put back together in a packet, and that packet is sent on its way. As I say, this is a bit of a cartoon. In practice, you'd have another stage of processing after the buffering for multicast copies and things like this. Is just to give you a representation of roughly how it works. From the programmer's view, though, the programmer doesn't care. The programmer doesn't care what the underlying machine looks like, just like you don't care about the x86 instruction set. You care about the things that you want it to do. So you really define 3 things. And this is the P4 language. You describe the headers that you want. That's in the middle. And so they're the data structures. What does an Ethernet header look like? What does an IPv4 header look like? What does an MPLS header look like? Whatever you need in your environment, you define it there. And then the parser program on the left is essentially a state machine that says how do you break apart the packets that you're expecting. And then the tables are what tables I'm going to match on, and then what actions am I going to perform, and then what's the control flow that's on the right-hand side. So a P4 program has these 3 components. If you've never seen a P4, actually, anyone here seen a P4 program? What my observation is that most people who see a P4 program, they go, oh, that's actually really obvious. Right? This is a language that just represents the control flow that you're already familiar with. So actually, to understand one, generally people can go from learning to contributing within a day. And we've seen this on numerous occasions. And that's really because we don't do that many different things in networking. There's a basic set of instructions, a basic set of operations that we do many, many different ways. But they're all based off a similar set of instructions. That's why this model works. Okay, so up until this point, I've sounded like a professor. It's all very esoteric and also very hypothetical, what happens in practice. I'm not actually here to promote Barefoot, but I want to tell you there's an existence proof of such a device, but there'll be more. There'll be more. This is just one example. Since about December of 2016, the Barefoot Tofino chip, the 64 ports of 100 gig or 260 ports of 25 gig, it's programmed in P4. Its internal structure is slightly different from what I just showed, but at a high level, it's the same. It has many more stages. There are various other paths. But essentially, you program it in P4. And because it's a feed-forward machine, if you write a program and it compiles, it will always run at line rate. It's a feed-forward machine. There isn't any other choice. So it's kind of interesting. You don't have to worry about corner cases or strange different paths based on exceptions. It always runs at line rate. So it's very, very easy to program a machine like this. And there'll be more machines that come from other people that have a similar kind of model, and that's good. Because it means that we can learn one language and then reapply that skill that we've learned to program it to other devices. Here was the thing that was the surprise. I wrote a paper along with some people from TI back in 2013 that predicted that if you would design a chip like this, it would consume about 10 to 15% more power and take up about 10 to 15% more area. Intuitively, it makes sense, right? Seems as though it's programmable, you have to pay a penalty for that. And that was our prediction at 28 nanometers. I'm going to explain in a minute that there's something special that happens as you make the transition from 28 nanometers to 16 nanometers. The stack levels go up. The logic becomes very, very small. The difference actually goes away. So this device actually has the same power and the same cost as if it was fixed function. The logic goes under the wires. This is here to stay. The cost of making something programmable rather than fixed, the difference, the additional cost has gone to 0. There is no longer any penalty. What that means is in future, you'll be faced with the choice of do you build something that's fixed or something that's programmable. It's kind of obvious which you would choose if there's no difference between them in cost or power. One observation that I wanted to make You've probably seen there have been a couple of announcements of using these chips. I don't want to go through all of that. I'll leave Arista and Cisco to do that. One thing I want to point out, that both of them point out the benefit that gives them, the red oval moved, it should have been over multiple profiles. I don't know how that happened. Just imagine that's over here. The key here is it gives a path to differentiation. Right? It gives a path to be able to differentiate products that you can go head-to-head with the same silicon and actually sell things with different features. That's what competition is, then that's what this makes possible. So why will they be programmable? What is it that actually that means that they're the same power, the same cost, the same performance as the fixed function? So I'll just tell you a little bit of a story. Okay. These are 3 chips, the public digraphs for 3 particular chips that were all produced in about 2011, roughly. If we look at those chips, we'll see that the serial I/O, that of the chip that they dedicate to the outside world to communicate through serial links, is about 30%. And this has been roughly true over several generations of switch chip, 25, 30% for a long, long time. This is true whether they are fixed function, like the one in the middle, or programmable to some extent, like the ones on the edges. That's because it's just dictated by the speed at which they need to talk to the outside world. That's also true of later generations, too. Let's think about what happens to that I/O over time with Moore's law. So, or put another way, why doesn't it get less? Doesn't Moore's law make everything smaller? Well, with each successive generation, Moore's law will halve it, but then we're greedy. The only reason we're building a new generation is because we want twice the speed. So we gobble up the benefit, and lo and behold, we're back to where we started. That's when Moore's law is working. So the area stays the same over time through successive generations, and as a consequence, the serial I/O has stayed the same area for each generation for a period of about 20 years. Now let's look at the rest of the chip. The rest of the chip is packet processing and packet buffers and traffic management. So the packet processing consists of the tables that we look up, that's memory, and then the logic to do that packet processing. This is an assumption, it varies by chip as to what these percentages are. Here is one particular example, but let's look at the memory. The memory being the lookup tables and the packet buffers. Let's see what happens over time. Moore's law will give us a halving with each generation, but packet buffers we always want to double because we say the line rate has increased because the serial I/O got faster. And while we're at it, let's double the size of the lookup tables because we could always do with more of those. So it always means that we double the storage and we end up where we started from. So over successive generations, the memory has stayed the same. So I've now accounted for 75% of the chip, the memory and the serial I/O. They're independent of whether it's fixed function or programmable. Doesn't make any difference. That is all going to stay roughly that percentage over time. So it's the logic that dictates whether the device is fixed function or programmable. It's in the logic. Now, this is an important thing to notice. Do we double the number of features in each successive generation? No, we don't. Moore's law halves what it takes, but we increase the number of features by maybe 5%. All right, so the typical switching chip today, maybe it supports 45 or 50 different features. It's not going to go to 90 in the next generation. So it means that Moore's law will work in our favor. And so with, say, 10% new features, it will reduce the amount that goes into each one over time. And the logic becomes a smaller and smaller fraction with each generation. So that is shrunk over time. If this is true, we would expect the chips to look more and more uniform because the logic looks like spaghetti. The serial I/O looks like a ring, memory just looks like memory, a flat array, and the logic just looks like spaghetti. Well, look at the progression over time. They become more and more uniform. And in fact, if you look under a digraph, under a microscope for these devices, then what you find is the logic just gradually disappears. It becomes smaller and smaller and smaller, and then it disappears under the wires. And that is why now it's free to have that programmability, because the difference has gone away. And why in each successive generation from now on, that is true too. So how's it being used? Now, hopefully I've told you that at some kind of high level, wouldn't it be nice? There's a structure that says, hey, this seems kind of work. and there's an existence proof, and I've hopefully explained why maybe this will keep happening in the future. I haven't yet told you how anybody uses it. So I've had the benefit of having, through Barefoot, having kind of a ringside seat and watching how both researchers in universities, but also people in switch companies and cloud providers around the world have started to use it. So the thing that you probably are imagining is I'm going to give you a long list of features of things that people add. And I am in a minute. But first, I want to tell you the thing that surprised me. The first thing they do is they throw stuff out. They want to reduce complexity. This is by far the biggest first usage. So they say, I look at a fixed function switching chip. It has, say, maybe 45 features. I only use 4 of them in my network. Why do I need the other 41? They're consuming resources. They're consuming memory. They're consuming bandwidth. They're making me scared because they might go wrong and I don't have the expertise to fix them. Why can't I just remove that stuff? And so this is typically what people do. So the P4 community, with some help from many people, has developed something called switch.p4. It's a set of features and protocols defined in the P4 language, representing pretty much all the features you would expect to see in a cloud, a WAN, or an enterprise. It's available. You can read it. It's about 5,000 lines of code, so it's more than a day's work, but it's a couple of days' work. It's actually pretty easy to understand. Let's say that you are a cloud provider and you want 3 features. You want IPv4, let's say you want VXLAN, and you want Ethernet. So what you do is you comment out everything that you don't need, and then, you comment out everything that you don't need in the source code, which means it doesn't get compiled, it's not running on the chip, it doesn't consume any resources for the features that you don't want. The resources that you have, the tables, the internal bandwidth, is 100% used for the 3 features that you want. And you no longer have the risk that the things that you don't need will break, and you won't have any expertise to fix them. So then you would take that, you would then end up with your own personalized, it could be Azure switch.p4 or Facebook's switch.p4. And then you compile that and put it onto the chip, and now it does just those features that you want. Now, I said that I was going to tell you about features that people are adding, not just the ones that they're taking away. So I'll give you a sort of a little list. But I do want to point out that the things that people do want to add kind of surprised me in the variety of different things that they were interested in adding. But first, what have people added in the past? This is what a protocol graph looked like about 20 years ago. Packet would come in, and you have to decide whether it was IPv4 or IPX. That was basically all you had to do. Over time, that's grown. And so we end up with a graph that looks like this today. You can't see everything that's in there, but if I just zoom in on a portion of it, this is the graph for I don't know where that went, sorry. The portion of the protocol graph for that switch.p4, taken from things that are done today. Multicast, or everything you can think of under the sun. So we've added a lot of stuff in the past, right? Much of which we don't need in any particular environment. Well, once people have boiled down to the set that they need, and then start adding back in the things that they want for their environment that are different from everybody else's, they do things that maybe are not that surprising. They will add new encapsulations. I've seen a lot of different tailored private encapsulations, some that might be weird things like 18 bits long, 22 bits long. Who knows why they need to do it? That's what they do in their environment. New tunnel formats, new ways to tag packets for special treatment, whether that's in a cloud or it could be for security purposes. New approaches to routing. Source routing seems to be on the rise. As soon as you can actually decide how you allocate the tags at the edge, then people seem to want to do that, whether it's segment routing or some other type of private proprietary source routing technique. That seems very, very popular. New approaches to congestion control. Tagging packets as they go through to indicate how long they waited at each switch along the path in order to be able to inform the source how it changes the rate at which it sends. This seems to be quite popular as well. New ways to process packets as they go through. One natural one is processing ticker symbols, but all sorts of variations for that for high-frequency trading. To give you just a couple of examples, one is, in a sense, fairly obvious, layer 4 load balancing. A device that is capable of doing stateful processing on a large number of flows, like Tofino, can be programmed using P4 to do layer 4 load balancing in many different environments. So it's typically replacing a hardware load balancer or a software load balancer. Hardware load balancers, we know what they do. Incoming flows, like an HTTP flow, would come in. It would go to some load balancer that would determine the server that's going to process it. We require lots of expensive boxes. We require diverting the traffic away from the main flow. If you do it in software, then they are CPUs that could be used for selling to customers and renting to customers for revenue. It is said that roughly 5 to 10% of the CPUs in some data centers, in some cloud data centers, are used just for load balancing incoming traffic across the rest of the fleet. So what if instead of having to have all of those servers, we could just turn that top of rack switch, or whatever that switch, by adding a P4 program and turn it into the load balancer? Okay? And therefore eliminate it, and all it's simply doing is deciding the server. What does it need to do? It needs stateful processing to keep track of the flows. It needs to keep track of the servers as they come and go to make sure that you're consistent in the way that you map it. Okay? This is now actually deployed, commercially deployed in a number of places, doing exactly this. So you can typically replace at least 200 servers with one switch, and that switch could just simply be the top of rack switch that you were using anyway. And in this particular example, it was demonstrated up to about 10 million HTTP flows. It's actually described in a paper that was published last year. Another one that's a little bit more esoteric that I thought was kind of interesting, and this was for key value store cache. Right? So this definitely goes into the realm of the more esoteric, but it'll make you think. Think of something like memcache, where you have a number of servers over which you've sharded a large key value store. Why do you have a large number of servers? You have a large number of servers, A, because there's too much stuff to put on one, and B, that if one of them fails, you want to make sure the whole thing doesn't go out. So for both the scaling and the redundancy. So you may have a read rate into that key value store, let's say at rate R, and hopefully you've got at least capacity R in the links connecting that switch to the servers, otherwise you're not going to get started. Typically, you have a multiple of that because of hotness. There will be some entries that are hotter than others. And it's the hot entries that cause the long tail latencies of a key value store. Let's say that you've got entries that are particularly hot on 2 of them right now. You can immediately see that the capacity or the total throughput could be reduced quickly to R times 2 over n, where n may be 100. You've taken a tiny fraction of it, and that's why you see the very long tail latencies. What do you do typically in that case? You make n larger, and you make more copies in order to prevent this happening. But actually making the copies fast enough is very, very hard. This is the predominant reason for large tail latencies in these key value servers, key value stores. So what if we were able to put a cache in front of it? So you've got a cache, a memcache, and you put a cache in front of it. Well, there isn't actually a storage device or a computation device that's fast enough, because if there was, you'd have used it to build the memcache in the first place. But there is one device that's sitting in there that is fast enough, and it's the switch. And we don't normally think of the switch as being a place where you'd put a cache. Right? It seems a bit weird. But what if you did? So you wrote a P4 program, and what it would do is it look at the key value store, and then it would figure out whether it can actually serve it from a local cache inside the on-chip memory. Sounds crazy, right? There can't possibly be enough memory on the chip in order to be able to do that. Turns out that in a surprisingly large number of cases, there is. And this is because of a result that from a few years ago that said, and if you think about this for a moment, you'll see that this has to be true. The size of the cache has got nothing to do with the key value store size. It's a function of n, the number of servers over which you've spread, because that's the hotness imbalance. And so order on n log n, and n is typically of the order of 100, is actually quite adequate to reduce the tail latency by about 95%. The question is, how big is the size of the entry that you need to put in there? Well, in many, many cases, it's very small. And actually, you can easily fit this into the on-chip memory of a switching chip. And so there have been cases of people beginning to do this. Is this going to work everywhere? I don't know. I don't build big key value stores. But it's the kind of example of once you've got a programmable element, people start to do things that you didn't expect, because they can offload things into this very high throughput environment with a fixed guaranteed latency that gives them the performance that they were looking for. So if you want to read more about it, there's a paper that was actually in SOSP from last year that explained this. Other offloading things that I've seen, some of them are, you would guess, some of them not. Fast firewalls, DNS caches. Turns out you could cache the entire Akamai or Netflix lookups for DNS lookups in one of these chips. Pub sub service for ticker symbol forwarding for HFT, etc. Going down the list here. Some with for training for machine learning, where people want to do parameter servers that will accelerate the machine learning training. There's a very healthy business going on at the moment in trying to figure out how to use the network and these programmable devices to accelerate parameter servers. I've broken out into a separate category of use network telemetry. And that's because network telemetry has probably provided the biggest initial pool for this kind of device, this kind of approach, and this programmable approach. And it took me a while to realize why that was. Because telemetry, everybody's talked for a long time about how difficult it is to see what networks are doing in order to be able to debug them. Right? I could have stood here 10 years ago, any of us could have stood here 10 years ago and said, isn't network measurement totally broken? We're still using traceroute and ping and SNMP. They're the same things we were using 20 years ago. Why is it that we can't actually do anything better than that when this is such a critical infrastructure? So why do we have to wait until the element itself is programmable before we do it? And I think the reason is this. We all have networks that operate in slightly different ways. And if you want to put measurement, as in telemetry, into the packets, by now, the networks have evolved such that you need to put it in a different place in almost every different network for it to work, because it's got to pass by without breaking anything. It's a little bit like the NAT problem on steroids. So how do you place it in the right location? If you're building a fixed function device, you've got to figure out where all the possible locations are that anybody in the world might put it, and then be able to support all of them. That is not possible. And so I know with one equipment vendor having the conversation with them about 15 years ago about doing this, and they didn't go down that path. They said we couldn't support all of the different formats that we would need to do. As soon as it's programmable, you have a fixed way of doing it, but then you can move it around wherever location you want, depending on the environment in which you operate. And so it's not that it's particularly clever to do the measurement, it's having the flexibility to place the measurement wherever you want so it doesn't break anything. Let me try and make this a little bit more concrete in the time that I have left. Imagine in this kind of environment, you want to understand how this network operates. You've got packets that are flowing in this network along this particular path. Here are the packets. Imagine you're coming into it and you're trying to wonder, how is this packet, how is this network operating? I believe that there are 4 questions that we should take for granted that we can answer, that today we cannot. The first one is, I feel I should be able to look at a packet and ask that packet, which path did that packet take? Networks don't allow you to do this today. You can send a traceroute and find out the path that packet took. It doesn't tell you what the packets took in the network. Why can't I actually have it tell me that, for example, I visited this switch at this time, etc., and then be able to record that and say, I know the path that it took. Now I know how it got here. It seems kind of obvious from a logging point of view that I want to be able to ask that of a packet. I might also want to know not only how it got here, but why did it get here, particularly if I'm interested in security. In other words, which rules did my packet follow in the switches along the path in order to get here so I can figure out how the hell it got here. Maybe it didn't belong here and I want to know how it got here. Well, the switch knows this. The switch actually follows a set of rules that I put there in the first place, and the packet should be able to tell me. Why can't it tell me in switch 1 I followed this rule, in switch 2 I followed this rule, etc.? Right? That would seem like 2 basic questions to be able to understand the functional behavior of the network. Networks don't do this. Now let's think about performance. What do I care about in performance? Queues. Stuff that gets stuck in queues for variable amounts of time. I can neither measure how long they were in the queue or why they were in the queue. But what are the questions I need to answer in order to be able to understand that? The first one would be, how long did my packet stay in a queue? Why can't the packet tell me I was delayed by this much at the first queue, this much at the next one, and this much at the last one? I've highlighted this one in red because that's a big value. That's a scary value, right? Because there's a natural consequence of this one. That value is too big. What happened? It could be a microburst. It could be a sustained aggressor. I want to ask the next question of the switch, which is give me the time series of the occupancy for all the packets that went through so I can figure out what went wrong. Whose fault was it? Who do I need to go and choke in order to be able to stop this from happening? It could be that there is some other packet that I shared the queue with. So who did my packet share the queue with? So who do I need to go and blame? Could be that mine, the green one at the bottom, were fine. They didn't do anything wrong. It's this orange one that I'm looking for. And so there's this aggressor flow somewhere sitting out there, this elephant flow that I'm trying to find. Why can't I do this? So there are basically 4 questions that I say that are ground truths that I should be able to answer in any network. Which path did my packet take? Which rule did it follow? How long did it queue at each switch? Who did it share the queues with? Networks today do not allow you to do this with a device like this type class of device. Doesn't matter whether it's this particular device. With INT, the inbound network telemetry, you can answer all 4 of those questions for the first time at line rate in every packet without generating additional packets. Right? You'll start to see this more broadly used because hopefully it will become more of a standard over time. To tell you how it works, all it's doing is taking information that the switch already had and has had forever and making it available through the data path to the endpoint. So as packets go through, adding things like the switch ID, the arrival time, the queuing delay, the matched rules, etc., adding those into the packet under your choice as to how much gets added. And then as you go through accumulating that information, you don't want to give that to the end host because the application might break or the host might fall over. So stripping that off at the end and sending it to a logging, analyzing, or a visualizing tool that will help you understand that. So take that off and send the original packet onto the end host. Now, a number of people are building systems like this. Barefoot has a thing called Deep Insight that they wanted me to mention, but I'll leave it at that, except to show you a screenshot of, at the end, of how that works. The key here is you need an open format to encourage a rich ecosystem of these kind of devices, of the monitoring systems at the end, such that a variety of different sources, whether they're NICs or switches or end hosts, can generate the format. So the detail format, or data plane telemetry format, which was recently released in Sonic, is trying to do exactly to do that, to make it an open standard under the auspices of p4.org. So look for that in the future. The sorts of things that you would be able to see with a device like this. This is looking at a microburst. So this is less than a microsecond in the life of this switch, the entire graph there. It's every single packet going into the queue. The different colors represent the flow that it belonged to, every event in and out of that queue, captured and then reported and then visualized at the end. The control plane never saw a single thing happen. All happened through the forwarding plane and through the data plane, just simply by tagging the packets as they go through. So you can imagine with that kind of visibility, you can go in and figure out what went wrong, whose fault it was, which applications were to blame. So in summary, how is that programmability being used? Reducing complexity, adding new features, and network telemetry, and you'll see more of that over time. One last comment about ecosystem, and that is the P4 language and p4.org. The P4 language, which is now in its second incarnation as P4.16. P4.16 was a progression over P4.14, which is a predecessor language, which was somewhat tied to the PISA architecture. But there was so much interest in adding this programmability to kernels, to NICs, to FPGAs, to other types of switch architecture, that the community came together and developed P4.16 in a way that you feed into the compiler the architecture of the device and the program, and then it will compile down to that particular device. There's now support for a variety of different targets. P4.16 is clean. It's very simple with strong typing. It's available under a permissive Apache license. And really, at this point, it's become kind of the de facto industry standard language. There are more improvements, including targeting NICs that you'll see, adding traffic management and scheduling over time. The community was set up as an open source community in the most genuine form. No barrier to entry, free membership, simple licensing, board governance model, very straightforward, very standard. We've now merged this with the Open Networking Foundation and the Linux Foundation. And as you probably have seen, we have regular tutorials and workshops. The P4 language was originally created by a number of companies represented here, but at this point, there are over 100 companies who are members. If your company is not on the list, I'd encourage you to take part. What we're trying to do is to create a standard language. You learn it once, and then you use it on all the different devices that do packet forwarding in your network. So pretty much all of the key players in our industry are involved. The end users, the system companies, the targets, the switch chips. Barefoot, Broadcom, Cavium, Intel, etc., all involved in this consortium. You can get involved, go to p4.org. You'll find plenty of resources there to help you learn about the language. And please, attend the tutorials. Come to the workshops, the developers' days. I know some of you have attended them. And you can participate in the working group activities. They're all open. And then bring your own expertise. There are new compilers that have been contributed from other people, new tools, new development environments that are being contributed, formal verification, equivalence check, etc. We need more of those. Please bring them over time. In summary, I really do believe that SDN is about changing who is in charge. No, as far as I know, no one that designs chips for a living operates big networks. So why are they defining the behavior of your network? You should be defining the behavior of your network. You write the software to control it. Now write the software to control how it processes packets. Because all the network does is move packets from one place to another. You should define how that behavior takes place. The chip technology has moved to the point where that's now doable at no additional cost. We now have line rate telemetry as an example of something that you can bring in. And it allows you to bring in your ideas that you can create things that are different in your network. And you don't need to share them with me or anybody else, because you own them, you differentiate, and you get to decide how that works, and you own those ideas for yourself. Thank you.
We have time for a couple questions.
So I'm just wondering, is there a standard way by which the control plane interacts with the data plane functions that you implement using something like Barefoot?
Yeah, so there's been a lot of work and a lot of people thinking about the interaction between the forwarding plane, the switches, and their control plane, whether that control plane is resident on the switch or off the switch, and different people choose to do that in different ways. So it used to be that they were sort of closed proprietary APIs. We're moving away from that generally. You remember OpenFlow, it was an attempt to move in that direction. I'd say that it was turned out to be too rigid for what it was trying to do. So you'll see, for example, in Sonic, a lot of work to try and massage and get that API to be as simple as possible, to make it as easy as possible to create new functionality on top, to exploit whatever the switching chips can do. And if you need to actually enhance it, then it's an obvious place to enhance it. So open APIs is definitely the direction we're going in. There's also a move towards making them programmatic, the API itself. Because if the underlying chip is programmable, it has no natural API. You can define the API for whatever you want. And so it allows you to have an API which is extensible by default. And so there's something called P4 runtime, which is an attempt to extend and enhance it just by simply saying, I've now changed the P4 program that changes its behavior. I've now extended that API. So we're seeing a whole gamut of open, extensible APIs evolve. And I think we're going to see that happen over the next few years.
Okay, but usually there's a lot of assumptions other than how the API looks. For example, when you're dealing with a certain protocol, you may have a specific punt rate. You know, how many packets do you want to punt to the control plane to be able to do a certain function? What types of signaling are you sending to the control plane?
Sure.
Is there a standard way to do that so that no matter what data plane modification you do, you always use kind of like the same interaction between control plane and data plane, so you don't have to reinvent this every time?
So the SAI interface, the switch abstraction interface in Sonic, is a large piece of that puzzle in terms of having a way that would work with a variety of different silicon for a given OS, Sonic, right? P4 runtime is attempting to do the same thing in a way where it will run on a variety of different silicon where you've expressed the behavior in that P4 program. As you enhance that, it would extend and enhance that API. So you can say, hey, I'm adding BGP in now, or I'm adding MPLS, or I'm adding my own proprietary protocol. You would add that, and then the API would extend and enhance in order to do that. So I think you can see in all of these environments that will start to happen. Is it ready available today? No, it's kind of just in progress of happening now. And to the extent to which it will be exposed up to the cloud customer, that's way off. That's not happening anytime soon.
I have one question, Nick.
Yeah.
So you talked about domain-specific language for networking. Yet some of the examples you showed are very generic, pub sub, key value store. So what can you do or not do with this domain specific language for networking? Like, can you do any function or?
No, you can't, and that's what domain-specific languages are for, right? They're for specific type of processing that lends itself to match action, state update, and a little bit of state maintenance. But they're about high throughput, low latency state management, and this is what the P4 language is sort of designed for. All of those applications are of that form. So look at DNS caching. What is a DNS cache? It's a lookup table. And it has different dynamics, it has different entries, but essentially it's just a lookup table. And so the DNS cache gets updated in a different way, in a different manner, but as far as the underlying switch, as long as you can express it in that P4 language, it'll run at the same line rate, and that's how it works. So they all have that characteristic to them, like load balancing, right? Flow maintenance, being able to throw them out, add new ones, and doing the state update in the pipeline. So they all have that flavor to them. And what surprised me is that there are a lot more applications that either entirely have that behavior than I had known, or there are ones for which the bottleneck has that behavior. And so you could take the bottleneck and use the network to accelerate it. So machine learning training as a parameter server. There's a lot of the interleaving of parameters and the update of parameters that you can put right into the network because they have that nature to it. It's not standard protocols, but it's close enough and has the same kind of match action behavior that you can express it and do it that way. And I suspect that there are thousands more that none of us have ever thought of.
Okay, let's thank Nick.
Do you have one more? Ready?
So you described Act 1 and Act 2 of SDN. What's Act 3?
The beach, maybe? I don't know. I don't know. I'm far too old to think of anything new. That'll be up to you. Thank you.
Thank you, Nick.